Okay, here we are, starting chapter 3. This is constant change in the graph of y equals mx plus b. Here's your first journal choice of the chapter. I'm kind of excited to get this chapter going. It's a lot of review. It's good Algebra 2 stuff, things you've seen before, so I think you're going to like it. Objective and what's the point? Show how the slope-intercept form of a linear function arises naturally from situations of constant increase or decrease. And we're going to review this graphing lines and using slope and y-intercept. This first sentence, what it says, arising naturally from situations of constant increase or decrease. A lot of word problems follow a linear relationship, and we're going to try to find a way that we can notice it right away. We're going to determine slope and intercepts of a line given its equations, recognize properties of linear functions, model constant increase and decrease situations, and graph or interpret graphs of linear equations. Most of this is review. Basically what we're going to do is throw in the word function when we're talking about this stuff, this section. But I think you'll think this section is pretty easy. I'm going to go over a lot of vocab. Some of it you already know. Hopefully most of it you already know. So you should be able to get through this notes relatively quickly if you just read the and fast forward what you don't need explanation on. Okay, words to know. Y-intercept, I think you guys all know what the y-intercept is. It's where it crosses, the line crosses the y-axis. Here's your y-axis. So this would be our y-intercept, this point right here. The x-coordinate's always 0. We abbreviate it with the letter B a lot. I don't know where that came from. I think I've looked it up before. I might look it up before class tomorrow. But it's also usually the initial condition in a lot of situations. The reason it's the initial condition, if you think about it, is because a lot of times initial is kind of referring to time. A lot of times linear relationships are graphed against time for the x-axis. And at 0, this is what time would start, and that is the initial time. A lot of times will be up in the positive vicinity. It doesn't have to be, but a lot of real life situations are looking at quadrants 1 or 1 and 4. So that's why that y-intercept has a lot of significant meanings in real world problems. Slope. Our slope is the rate of change. We've talked about this before. All lines, you should know from geometry, are congruent, really, because there's no starting and end point. They go on forever. There's no width, so we can map every line on top of another line. So we need a way to distinguish them from each other, and the way we distinguish one line from another is using this measurement called slope. It's the rate of change. It's the steepness of the line. We abbreviate it with the letter M. I think you know this. And it is the increase or decrease per unit. And we kind of touched on that last chapter whenever we were saying from the speeds this to this, the rate of increase was this, okay? Very much related to the rate of change we talked about with direct variation. The x-intercept, I don't think kids use as much. It doesn't have a meaning in all problems, because not all problems will have an x-intercept if you're looking at real world situations. X-intercepts where it crosses the x-axis, which is right here. Here's your x-axis. And I think most of you will like it because it's an easy value to find when you're trying to find 2 points. If you plug in 0 for y, you can get the x-axis, x-intercept, excuse me. Just like whenever you're looking for the y-intercept, you can plug x equals to 0. This does have real world situations, which we'll talk about later. Basically when you run out of something. More words. A linear function. We've talked about functions already. You know what they are. If you don't by this point, I'm a little crabby with you. It's a function whose graph is a line or part of a line if it's a linear function. But the key word is it has to be a function. What are those functions? For every x, there is only one y. So I'm asking you, are all types of lines linear functions? I want you to think about that for a second. The answer is no. There is one line that's not a function. And I think you can figure out which one it is when you remember the other way you could test. You're testing to see if something's a function by checking the x's, that's one way, or the one that a lot of you like the most, the vertical line test. I'm pretty confident a vertical line will not pass its own test. I should go pink. Because if I draw a vertical line here, oh my gosh, they're touching everywhere. Okay, because for that x value there is multiple y values. So there's one line that's not a function, and that is your vertical line. And this should also make sense, especially those of you who have the TI Inspires. the 84 people, when they want to graph something, it says y equals. TI Inspire people says f of x equals. Okay? Because your graphing calculator only knows how to graph functions, that's not entirely true at the TI Inspires, but I haven't showed you how to change that yet. It has to have y equals. The equation of a vertical line is x equals a number. You can't type that in your calculator because your calculator only graphs functions. X equals a number is not a function. Okay, I am going to go out on a limb and say slope-intercept form is the most important formula you'll ever learn in your algebra career. Because a lot of the other really important ones you could get by without if you know this one really, really well. Y equals mx plus b. You need to be good at this. If you are struggling at all with y equals mx plus b, I encourage you to get help because you're going to have a hard time in the rest of your math career. Okay? This is an equation for lines. It's ready to graph form. I can graph a line super, super quickly if I have an equation in this form. This is very nice because when y is by itself, m, the slope, is smushed right up against the x. So you can notice it quickly and you have it handy. Everything that's left after the x term, this constant, this will represent your y-intercept, including its sign. So then the only two things I need, I start like where b is, and then I jump into my slope, and I could graph the thing very quickly. Okay? It's also very quickly for coming up with equations if you know certain things about a graph. We'll do lots of practice with that. Enough of the words never. I have a few more. Here, I'm really proud of this diagram. I just want to tell you guys this. Before I figured out you could copy and paste pictures, I made every one of these lines like separate. So you can go ahead and take a nice look at that and think, wow, my teacher is special. Constant increase situation, this is it. Usually we are talking about quadrant 1 with these. Not always. Sometimes it can be 1 and 4, I suppose. But almost always it's going to be 1. This is what I was talking about when you're graphing against time a lot. It doesn't have to be time, but usually. This initial condition is your y-intercept. This is where it's starting. And this is a constant increase situation because as you can see, the quantity is increasing, okay, as a positive slope. You can always tell what it is because of the slope is positive. So I know that now you're ready to guess. Constant decrease. Still has the initial condition, very significant. That's your y-intercept, your b value. But this time the situation is decreasing. It has a negative slope. Now you notice here that you have a x-intercept. In this situation you didn't. Okay, and that will come into play later. So it's just something to take notice of. Alright, this is it for the words for today. Parallel lines. You talked about this in geometry. They have the same slope. It is very important. They are a translation of each other. So if I have a line here, a parallel line could be down here. I know they are parallel only if they have the same slope or the same rate of change. They will never touch because that rate of change is the same, so they will not intersect. This theorem is basically saying if you know lines are parallel, then you know their slopes are the same. If you know two slopes are the same, then you know they are parallel. This if and only if, you know, from geometry, makes things go back and forth. This can be proven using the side angle side and angle side postulates. You can look on page 153 if you're interested in that proof. Some of you are thinking about taking math further into college. You should start looking at those proofs because they start you off with some really nice ones here. It's not going to be pertinent to everyone though, so I didn't require it. Okay, so let's look at a couple examples. A pool containing 85 gallons of water. Well, that's a fragment. I guess suppose a pool. Or a pool can contain 85 gallons of water. Don't tell Miss Morgan. Suppose a hose adds water to the pool at a rate of 7 gallons per minute. Write an equation for a function. So we're going to start using this function notation like I told you about, representing the amount of water in the pool t minutes after the hose is turned on. The pool can hold this much gallons of water. Okay, here's how these go. The first thing we do is we name our function, and I usually name it something that's significant, and I take a look at the variables. If I'm looking for variables here, I have t for minutes, and what's the other quantity we're talking about? Amount of water. So I named it water. Okay, W of t is the amount of water after t minutes. I think actually this will be the hardest part, naming your function for you guys today, because that's the only real new thing here. Then you think about what's happening here, okay? So I have the amount in the pool to start. This is also called our initial condition. And then we're adding stuff to it, which that would be our rate of change. Since we are adding to it, that'll be a positive addition. It's going to be a constant increase. Okay? I don't even know. Come on, come on, come on, come on. I'll just move her down here as far as I can. Okay. Fill in what we know. We know what 85 gallons was that initial condition. What was the rate of change? 7 gallons per minute. I'm going to tell you guys right now, if you see the word per, that's a big indicator that that's your rate of change or your slope. Because that's a comparison of units. And remember, slope is rise over run. That's a division problem. Miles per hour, that's a rate of change. Gallons per minute, that's a rate of change. Okay? So this 7 is the rate of change we're talking about. That rate of change is changing with respect to what? Time. This also, the minute, that's telling you what goes below. That will tell you what your quantity is here. So here's our function. W of t equals 85, the initial condition, plus 7t. Notice this is not how we used to write these. A lot of you would have wrote W of t equals 7t plus 85. That's okay, except it doesn't make as much sense when you're writing it. What did I start with? What am I adding? This is saying what I'm adding, and here's what I start with, by the way. This is in mx plus b form. It's probably nicer for you to graph it this way. It's more familiar. But this makes more sense when writing it, I think. Okay, I don't care how you do it. A mudslide. Oh my gosh, those are very fascinating to me. They left 42 acre-feet of mud in a valley. We talked about this acre-foot last year. My students were like, what's an acre-foot? And then we asked Mr. Getton. And it's a lot, if you think about it. It's a 1 full acre. So if somebody lives on an acre lot of 1 foot deep, that's an acre-foot. So 42 acre-feet of mud. Think about that. It's a lot of mud. So it left it's a quantity, volume. It left it in a valley. The mud is being removed at a rate of 5 acre-feet per day. So, a linear equation to model the situation. M of t, mud after time, days. Again, we have this initial condition. We have this 42 to start with. This time we're taking out mud. So this is going to be a negative slope, constant decrease. 5 acre-feet per day. Again, per, that word there, helps us out. This is trickier. When will the mud be removed? When will it be removed? Well, we're looking for time. When is the question of when time. We are going to let m of t equal 0. That is when the mud will be removed. Okay, so I have 0 equals 45 minus 5t. I'm confident you guys know how to do this, but I'm going to go ahead and write up here anyway. 0 equals 45 minus 5t. Subtract 45. Negative 45. Don't lose your negative sign here. Divide by negative 5. Divide by negative 5. And you get 8.4. So the mud will be gone in 8.4 days. We know it was days because that was the rate they were talking about. Okay, this is fun. I know you like it. I'm glad. Okay, back to the mud. What are the y-intercept and the slope of the line represented by the equation? Okay. I think that's helpful to actually graph it first. So we're going to start here with the second part. The equation that we just wrote, I forgot it, was 42 minus 5t. M of t equals 42 minus 5t. If I graph this, it's the same thing as m of t equals negative 5t plus 42. My y-intercept is 42. My slope is negative 5. Okay, your graphic calculator can handle this. This is what the graph looks like. This is really sloppy. I apologize. Here is 0.42 is our y-intercept. That's your b. Your slope, down 5 over 1, down 5 over 1 all the time. We already figured this point out was 8.4. Okay, they want to know what this is representing. Okay, again, the y-intercept here is representing that initial condition. Where am I at when time is 0? Because this is time, remember? So time is 0. It's representing the initial value, that 42. That rate of change is the removal rate of the mud. That's the relationship between the graph and the equation. And that's all I have for today. We will go over our homework and get busy tomorrow. See ya.